This episode is brought to you by Cisco Educational Premium. Did you know that Lippmann-Schwinger equation is consistent with Schrodinger equation? The Lippmann-Schwinger equation is one of the most used equations to describe particle collisions, or more precisely, scattering in quantum mechanics. It may be used in scattering of molecules, atoms, neutrons, photons, or any other particles, and is important mainly in atomic, molecular, and optical physics, nuclear physics, and particle physics, but also for seismic scattering problems in geophysics. It relates the scattering wave function with the interaction that produces the scattering potential, and therefore allows calculation of the relevant experimental parameters, scattering amplitude and cross sections. The most fundamental equation to describe any quantum phenomenon, including scattering, is the Schrodinger equation. In physical problems, this differential equation must be solved with the input of an additional set of initial or boundary conditions for the specific physical system studied. The Lippmann-Schwinger equation is equivalent to the Schrodinger equation plus the typical boundary conditions for scattering problems. In order to embed the boundary conditions, the Lippmann-Schwinger equation must be written as an integral equation. For scattering problems, the Lippmann-Schwinger equation is often more convenient than the original Schrodinger equation. The Lippmann-Schwinger equation is useful in a very lineup of situations involving two-body scattering. For three or more colliding bodies, it does not work well because of the mathematical limitations. For diff equations may be used instead. However, there are approximations that can reduce a many-body problem to a two-body problems to a set of two-body problems in a variety of cases. For example, in a collision between electrons and molecules, there may be tens or hundreds of particles involved, but the phenomenon may be reduced to a two-body problem by describing all the molecule constituent particle potential together with the pseudo-potential. In these cases, the Lippmann-Schwinger equations may be used. Of course, the main motivation of these approaches are also the possibility of doing the calculation with much lower computational efforts. From the mathematical point of view, the Lippmann-Schwinger equation in coordinate representation is an integral equation of Fredholm type. It can be solved by discretization. Since this is equivalent to the differential time-independent Schrodinger equation with appropriate boundary conditions, it can also be solved by numerical methods for differential equations. In the case of the spherically symmetric potential V, it is usually solved by partial wave analysis. For high energies or weak potential, it can be solved perturbatively by means of bond series. The method convenient also in the case of many body physics, like in description of atomic, nuclear, or molecular collisions, is the method of the R matrix or Wigner and Eisenberg. Another class of methods is based on separable expansion of the potential of Green operator, like the method of continued fractions of Harach and Sasakawa. Very important class of methods is based on variational principles. For example, the Schwinger-Langossos method combining the variational principle of Schwinger with Langossos algorithm. In the S matrix formulation of particle physics, which was pioneered by John Archibald Wheeler, among others, all physical processes are modeled according to the following paradigm. One begins with a non-interacting multiparticle state in the distant past. Non-interacting does not mean that all of the forces have been turned off, in which case, for example, protons will fall apart, but rather that there exists an interaction-free Hamiltonian H naught for which the bound states have the same energy level spectrum as the actual Hamiltonian. Hamiltonian. This initial state is referred to as the in state. Intuitively, it consists of elementary particles or bound states that are sufficiently well separated that their interaction with each other are ignored. The idea is that whatever physical process one is trying to study will be modeled as scattering process of these well separated bound states. This process is described by the full Hamiltonian, but once it's over, all of the new elementary particles and new bound states separate again, and one finds a new non-interacting state called the out state. The S matrix is more symmetric under relativity than the Hamiltonian because it does not require a choice of time slices to define. This paradigm allows one to calculate the probabilities of all the processes that we have observed in 70 years of particle collider experiments with remarkable accuracy. But many interesting physical phenomena do not obviously fit into this paradigm. For example, if one wishes to consider the dynamics inside of a neutron star, sometimes one wants to know more than what it will finally decay into. In other words, one may be interested in measurements that are not in the asymptotic future. Sometimes an asymptotic past or future is not even available. For example, it is very possible that there is no past before the Big Bang. In 1960s, the S-matrix paradigm was elevated by many physicists to a fundamental law of nature. In S-matrix theory, it was stated that any quantity that one could measure should be found in the S-matrix for some process. This idea was inspired by the physical interpretation that S-matrix techniques could give to Feynman diagram restricted to the Mars shell and led to the construction of dual resonance models. But it was very controversial because it denied the validity of quantum field theory based on local fields and Hamiltonians. Intuitively, the slightly deformed eigenfunctions of the full Hamiltonian and in and out states, the phi are non-interacting states that resemble the in and out states in the infinite past and infinite future. This intuitive picture is not quite right because psi is an eigenfunction of the Hamiltonian. Psi raised to plus or minus is an eigenfunction of the Hamiltonian, and so at different times only differs by a phase. Thus, in particular, the physical state does not evolve, and so it cannot become non-interacting. This problem is easily circumvented by assembling psi raised to plus or minus and phi into wave packets with some distribution Ge of energies E over characteristic scale delta E. The uncertainty principle now allows the interactions of the asymptotic states to occur over a time scale reduce Planck constant on delta E. And in particular, it is no longer inconceivable that the interactions may turn off outside this interval. The following argument suggests that this is indeed the case. Plug the Lippmann-Schwinger equation into the definitions. Psi g raised to plus or minus t is equivalent to integral of dE ei e negative I et ge psi raised to plus or minus and psi gt is equivalent to integral dE e raised to negative I e t g e phi of the wave packets. We see that at a given time, the difference between psi gt and phi gt wave packets is given by an integral over the energy E. This integral may be evaluated by defining the wave function over the complex E plane and closing the E contour using a semicircle on which the wave functions vanish. The integral over the closed contour may be evaluated using the Cauchy integral theorem, a search of the residues at various poles. We will now argue that the residues of psi raised to plus or minus approach those of phi at time t approaching positive or negative infinity, and so the corresponding wave packets are equal at temporal infinity. In fact, for very positive terms t and e raised to negative iet factor in a Schrodinger picture state forces one to close the contour on the lower half plane. The pole in the phi psi from the Lippmann-Schwinger equation reflects the time uncertainty of the interaction, while that in the wave packets wave functions reflect the duration of the interaction. Both of these varieties of poles occur at finite imaginary energies and so are suppressed at very large terms. The pole in the energy difference in the denominator is on the upper half plane in the case of psi, and so does not lie inside the integral contour and does not contribute to the psi integral. The remainder is equal to the phi wave packet. Thus, at very late terms, psi will be equivalent to phi, and identifying psi as the asymptotic non-interacting out state. Similarly, one may integrate the wave packet corresponding with the psi, this one raised to a positive this term, at very negative terms. In this case, the contour needs to be closed over the upper half plane, which therefore measures the energy pole of psi, which is the lower half plane. One then finds that the psi and the phi wave packets are equal in asymptotic past, identifying psi as the asymptotic non-interacting in state. This identification of the psi's as asymptotic states is the justification of the plus or minus epsilon in the denominator of the Lippmann-Schwinger equations. The S matrix is defined to be the inner product. SAB is equivalent to psi raised to negative A plus psi raised to positive B of the earth and bith Eisenberg picture asymptotic states. One may obtain a formula relating the S matrix to the potential V using the above contour integral strategy, but this time switching the roles of positive psi and negative psi. As a result, the contour now pick up the energy pole. This can be related to the phi's if one uses the S matrix to swap the two psi's. Identifying the coefficients of the psi's on both sides of the equation, one finds the desired formula relating to the S potential. In the Born approximation, the corresponding to the first order perturbation theory, one replaces this last psi with the corresponding eigenfunction phi of the free Hamiltonian, yielding SAB is equivalent to sigma A minus B minus 2I pi sigma EA minus EB phi A V phi B, which expresses the S matrix entirely in terms of V and free Hamiltonian eigenfunctions. These formulas may in turn be used to calculate the reaction rate of the process B as it approaches A, which is equal to SAB minus sigma AB squared. With the use of the Green's function, the Lippmann-Schwinger equation has counterparts in homogenization theory, like mechanics, conductivity, and permittivity. This episode is brought to you by Cisco Educational Premium. In 1494, Luca Pacioli publishes Summa de Arithmetica, a comprehensive collection of all known mathematics in Renaissance Italy. In it, there is a section on the cubic equation. By this time, people have been trying to deduce the general solution of the cubic equation for at least 4,000 years. Each civilization that faced it would not conquer the cubic equation. So, reasonably, Pacioli's conclusion is that the solution to the cubic equation is simply impossible. Back in those days, mathematics was not written down in equations. It was wordy and at times poetic. People viewed mathematics literally. All mathematical concepts were drawn from the real world, and anything that could not add up was met with a lot of skepticism. Geometry was much loved as it described things that could be seen. Imagine you stepped in ancient Italy in the Renaissance period. You are a student attending some math class. You step on the door, then proceed to sit on that favorite chair and table of yours right by the corner. It is at that day of those cards again, and you have a mathematics test. The first question, you have been told to solve the quadratic equation. X squared plus 4x is equivalent to 12. Opposite to how you will complete the square algebraically, you will actually complete a literal square to solve the equation. You will be having some sort of manila paper. To solve the quadratic equation, you will cut a literal square with side x from your manila paper to represent the x squared part of the equation. After this, you will cut a rectangle of side x for the width and side 4 for the length. I will still remember that the equation equals 12. To solve this quadratic equation, you would cut your rectangle into two parts, each with width x and side 2. You would then reorganize these two rectangles with that first square with side x to form a bigger square with side 2x. This square is not complete. To complete it, you would need to add a square of side 2, which is missing in the middle. Then, because you have added 2 square on one side of the equation, you will also add another 2 square on the other side to get 16. So we have the big square being equal to 16. Then finding the square root of 16, you will find it to be 4, which will represent the side of the big square. As you can see, you can derive the value of x to be 2, because 2x is equivalent to 4. And so you would have solved the quadratic equation. Looks like you have a bright future in math. You have found the solution to be 2, right? But so is negative 6. You see, back in those days, you wouldn't consider negative 6 to be a solution because negative 6 will not be geometrically relevant. After all, how would you have a negative area? It doesn't make sense. In fact, contrary to these days where we have the quadratic formula x is equivalent to negative b plus or minus root b square minus 4ac on 2a to be the general solution to the quadratic equation. In those days, there was no general solution to the quadratic equation because those ancient ones had not accepted the idea of negative solution, especially the square root of a negative number. The same approach was taken for the cubic equation, with the search for a general solution bearing no fruit. No wonder Omar Khayyam wrote, "Maybe one of those who will come after us will succeed in finding it." Now comes another character in our story, Scipione del Ferro. Scipione del Ferro is a mathematics professor at the University of Bologna. Around the year 1508 to 1512, he finds a method to solve depressed cubics. What are depressed cubics?
Depressed cubics are a category of cubic equations with no x squared term. So what does it do after solving a problem that have obsessed mathematicians for thousands of years? One considered to be impossible by Leonardo da Vinci's math teacher? He tells nobody. You see, being a full-time mathematician is hard. If you don't find an opportunity in teaching, you would need to be publishing papers frequently to live off patents. In the 16th century, it was even harder. Your job would be constantly under threat from other mathematicians who can show up at any time and challenge you for your position. There was no particular formal certification or job guarantee. It was all decided on a duel, a math duel, if you are feeling fancy. So how is this math duel done? You can think of it like those math contests you had in high school. If you were fortunate enough to attend, or are fortunate enough to attend, but more like chess. It's a one-on-one game, except it's not a game this time. Your job, your source of livelihood is at stake. Each participant submits a set of questions to the other, and the person who solves the most questions correctly gets the job, while the other doesn't, and more serve as public humiliation. So far as Del Ferro knows, he is the smartest mathematician alive, so he guarantees his job security because no one else can solve the depressed cubics. For nearly 20 years, he keeps this secret. But as with human life, we are not immortal. Scipione is now a very old man in 1526, about to pass on. Before he passes, he breaks the secret to his super favorite student, Antonio Fiore, our third character in our story. Unlike Del Ferro, Fiore is not the smartest mathematician alive, nor is he the second or even the third. He's just a regular mathematician like you and I. Okay, maybe only like me. But Fiore is very ambitious, one of those guys who will build castles in their imaginations. After Del Ferro's death, he boasts about his mathematical ingenuity and even has the audacity to dare to be able to solve the depressed cubic equations. Remember that type of cubic equations? About this time, Niccolo Fontana Totalia, another mathematician, our fourth character, moves to Fiore's town of Venice. And just so he knows who is who in the town, at least in math, Fiore plans to challenge this new mathematician, Totalia, in math duel. Remember the math duel? On February 12th, 1535, Fiore challenges Niccolo Totalia on a math duel. Totalia is a diehard. As a kid, he survived an attack by a French soldier who left his face open by a cat. That's why he is named Totalia, which translates as stutterer in Italian. Growing up in poverty, Totalia is largely self-taught, one of those self-made guys. He claws up his way to the Italian society to become a renowned mathematician. Now all of this is at stake. As in the math duel, questions are exchanged to see who wins. The visitor Niccolo Totalia decides to take the lead. He gives Antonio Fiore 30 math questions, while Fiore, on the other hand, gives Totalia 30 questions, all of which are depressed cubics. Each mathematician has about a month for the days to solve the equations they have been given. Now here's the challenge. Who will win and who will lose? Oh my. A big surprise is that Niccolo Totalia, our hardened diehard, solves all of Fiore's questions in just 2 hours, while Antonio Fiore continues to attempt Totalia's questions. What's the hurry? There is like 40 days. Right, everybody? After 40 days, Fiore is unable to solve Totalia's questions, not even a single one. which should not come as a surprise since Fior wasn't that talented mathematician and was just hiding behind his teacher's work, Scipione del Ferro. And so Totalia becomes the math kingpin of the town and Fior has to abide. What a math jewel. We should have one of these fine days. But maybe no. So, coming to think of it, Del Ferro was the only man in the world who could solve depressed cubics. So how did Niccolo Totalia manage to solve the hardest problem known? How did he solve the depressed cubic equations? As the saying goes, necessity is the mother of invention. Because solving the depressed cubic equation was necessary for his career, Totalia had to become creative. He extends the idea of completing square into completing the cube. For example, he takes the cubic equation x cubed plus 9x is equivalent to 26. Drawing the analogy from before, we can think of x cubic as a cube with sides of length x. The 9x term is a cuboid of volume 9x and the whole thing adds to 26. So as before, we need to do a similar thing and complete the cube. Imagine extending 3 sides of our cube, a distance y. This will obviously create a larger cube with side z, z being equivalent to x plus y. So we have the original cube deep at the corner and we can break the new bigger cube into 7 shapes. There are 3 cuboids with side x by y and narrower cuboids with side x by y, and then finally a cube with volume y cubed. Totalia then rearranges the 6 cuboids into 1 cuboid with length 3y with z and height x. This cuboid represents the 9x in our cubic equation. So putting the big cube back together, we find that we are missing the small y cubed. So we can complete the cube by adding y cubed both sides of the equation. X cubed plus 9x plus y cubed is equivalent to 26 plus y cubed. X cubed plus 9x plus y cubed being z cubed 3yz is equivalent to 9. Now we have z cubed, the complete larger cube equivalent to 26 plus y cubed. Now we have 2 equations and 2 unknowns. The first equation is 3yz is equivalent to 9 and the second is z cubed is equivalent to 26 plus y cubed. By solving the first equation for z and substituting the second, we get z is equivalent to 3 on y. 3 on y cubed is equivalent to 26 plus y cubed. Then y cubed plus 26 is equivalent to 27 on y cubed, which is y raised to the 6th plus 26 y cubed is equivalent to 27. Y cubed being its own variable, we get y cubed square plus 26 y cubed is equivalent to 27, which is a quadratic equation and we know how to solve it. Even Fior or Pacioli knew how to solve it. And so from this we get y is equivalent to 1, z is equivalent to 3, x is equivalent to 2. This is the solution to the cubic equation. And so this is how Niccolo Totalia became the second smartest mathematician in the world. He summarizes this as a poem. Remember, algebraic notation has not been invented yet. Totalia's victory in the duel makes him a celebrity, much like Rihanna or Quavo, but in math. Mathematical community is eager to hear from him. Everyone wants his attention. Girolamo Cagano, our 5th character in the story, is a mathematician based on Milan. He too wants to hear from Niccolo Totalia, but as with celebrities, it's not easy to interact with one, and as they are usually adamant to hear anything from their fans and no one is more adamant as Totalia, as he is to the mathematicians around the world, especially Girolamo Cagano. He refuses to reveal even a single question from the competition. However, Cagano is persistent and he manages to box Totalia. On March 25th the same year, 1539, Cagano manages to lure Totalia to Milan, and Totalia tells Cagano about this method of solving the depressed cubic equation. But there was a catch. Aside from introducing Totalia to his wealthy benefactor, Cagano has to swear solemnly that he would not tell anyone the method. He wouldn't publish it in any way, and will only write it in cipher. And as Totalia quotes, so that after my death, no one shall be able to understand it. Girolamo Cagano begins playing with Totalia's method. Now that he has a way to solve the depressed cubic equation, he wants to find a solution to the full cubic equations, including x squared term, and he finds it. The problem is he can't publish it because of the solemn oath he gave to Totalia. And why does he want to publish it just like that? You see, Cagano is a doctor and doesn't need a math job to make ends meet, and for him the credit is more important than the secret. But then what gives? In 1542, Girolamo Cagano travels to Bologna, where he visits a mathematician who happens to be the son-in-law to Scipione del Ferro. Remember him? Our second character in our story? Cagano finds the solution in Del Ferro's old notebook that was shared with him during the visit, and it predated Totalia by decades. So now he can publish his work without violating the solemn promise he gave to Totalia. In 1545, Cagano publishes Ars Magna, the Great Art, an updated compendium of mathematics. In it, he acknowledges contributions of Del Ferro, Fior, and Totalia. However, Totalia is not happy with this. But maybe to keep this in mind, these guys are still using the geometric analogy to solve these equations. The problem came when Cagano encountered problems that involved the negatives. He asked Totalia about this, but he could not solve it too. After all, how could you complete a square by adding a negative area, or complete a cube by adding a negative volume? So what does Cagano do? He ignores the possibility, affirming that the square roots of negatives is as subtle as it is useless. Around 10 years later, our last character in our story, the Italian Raffaele Bombelli, solved these problems that involved the negatives. How did he do it? He stubbornly went through with the calculations using Cagano's method, disregarding the geometrical paradoxes that the square roots of negatives implied. He finds out that the square roots of negatives cannot be called positive or negative, and he lets it be its own type of number. It turns out that Cagano's method works if you stop being too literal and just abandon the geometrical analogy for a moment. This new number was later termed as imaginary number by René Descartes, and later Leonhard Euler introduces the imaginary number I being equivalent to root of -1, whose coordinates lies perpendicular to the real number line. Personally, I think it's the worst name ever. Imaginary, isn't it as real as any other number? This imaginary number, when coupled with a real number, gives us the complex number. Today, complex numbers forms the cornerstone of the mathematics that shape our world. From Euler's formula, e to the ix is equivalent to cos x plus I sin x, to Schrodinger's equation. C-square educational premium is a section of C-square educationals with content that is not hosted here. There are episodes ranging from long to short,
videos. Remember those good old shots of ours? They are there. So how do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.